Okay, good to go. Have a good session.
Okay, thank you. So welcome to the last day of the workshop, Matches Made in Heaven. And we're very happy to have as our last speaker, Katrina Liggett, who will talk about privacy as stability for generalization. So Katrina is a professor at the Hebrew University of Jerusalem. Before that, she was at Caltech. And before that, if I remember correctly, she was a postdoc at Cornell. Before that, she was a PhD student of Avram Blum at CMU. So Katrina has done a lot of work on computational aspects of econ and a lot of work on privacy, of course, and learning. And we're looking forward for hearing what she has to say. So if you have questions, please write them down in the chat and we'll see whether to stop in the middle and discuss them or wait till the end, but definitely use the chat to write down your question. So Katrina, the stage is yours.
Thanks for having me. I hear a little echo, so if anybody who's unmuted can mute themselves, that'd be great. So today, as Moni mentioned, I'll be talking about this title that doesn't quite make any sense to us yet, Privacy and Stability for Generalization. Hopefully that will make some more sense shortly. This work that I'll be talking about is not just my own work. I'll mention as we go along the many contributions of many people to our improved understanding of the issues at hand here. But the central result that I'll present here is a joint paper with Christopher Jung, Seth Neal, Aaron Roth, Saeed Sharifi, Mal Jardi, all of them who were at UPenn at the time. Seth has since just started at Harvard, and Moshe Schenfeld, a student of mine at Hebrew University. This is a paper that appeared this year at ITCS. So following on this sort of matches made in heaven theme, today what I'm going to do is I'm going to talk about a particular notion, differential privacy, that was born out of really sort of a cryptography tradition and perspective. And I'm going to tell you about some of the exciting connections that this notion has turned out to have in the realm of statistical validity. The intention is that this talk should be totally accessible, even if you've never heard of differential privacy before, and even if you have no background in machine learning. Okay, so that does not look like it's doing the right thing. Excuse me. Let me make it do the right thing. So the plan for today is first I'm going to tell you a little bit about differential privacy and some of the nice properties that it has. And then we're going to do what feels like a sort of total 180 switch. We're going to talk about something that at first blush sounds totally unrelated, the problem of adaptive data analysis, which is a pervasive problem in data-driven science and machine learning. And then we're going to bring the two of those pieces together. And I'm going to help you see how privacy, sort of interpreted as a stability notion, can be useful for solving some of these problems of adaptivity and data analysis. And at the end, time willing, we'll talk a little bit about some of the really interesting open problems and subsequent developments in this space. Okay, so let's dive in. The model that we're going to be working with today is one in which we have databases that consist of unordered collections of data elements. So we have some data domain, and the data elements are drawn from that domain. And a database is just a set of n elements from the data domain, okay? You should think of each element as belonging to a person, and a database is then a collection of n people's data. And we're going to be worrying about privacy because what we're going to want to do is we're going to want to take a collection of n people's data, and we're going to want to answer some sequence of queries on that data set. We're going to want those answers to be correct, but we're going to want to be able to somehow say something nice about the privacy of individuals who participate. Okay. So formally, we're going to model that as a situation in which we have some mechanism M that is given a database, and it takes a sequence of queries, and it generates in response to each of those queries some response. Right now, those responses are just from some arbitrary scripty R space, okay? So a mechanism is just some potentially randomized function that, given a database and given a query, returns a response. And you can give it another query, it'll return another response. Formally, where are those queries coming from? We're going to model those queries as being generated by some analyst, or if you prefer, your A can be an adversary. So we'll think of an analyst or an adversary as a black box that, given some history of responses to previous queries, generates the next query. Okay, so we can hook those two boxes up together if we want to live in a world in which a mechanism has access to a database and then interacts with an analyst. The analyst issues queries, the mechanism responds to them, and so on and so forth. The analyst issues another query, the mechanism responds. Okay, and then we can wrap that whole interaction between the mechanism and the analyst in a procedure that takes each of them as an input, so takes the M, takes the A, and also takes the database and runs the interaction inside. And what it releases is the resulting sequence of queries and responses. So we say that interact is a box that takes in a database, a mechanism, and an analyst. And what it returns is the generated sequence of queries and responses. And that's going to be sort of the view of what happens when we have this mechanism and this analyst interact given a particular database. Okay, so this is sort of the high-level model that we'll have in mind today. And now what I want to do is give you a little bit of sort of the background and history for differential privacy. So the foundations of rigorous mathematical reasoning about this sort of process, this interaction of answering queries on a database, and the risks that it entails, were born of a landmark paper of Dinur and Nissim, where they gave us a number of things. They gave us sort of, first of all, a vocabulary for talking about issues like what is privacy, or in particular, what is not privacy, or what is privacy not. So one of the notions that comes from this paper is this definition of blatant non-privacy, which says that a mechanism is blatantly non-private if, when given a database and given the output that it generates, you can use that output to generate some other database that is extremely close to the original database. Clearly, if your mechanism has this property that its output can be used basically to reconstruct the underlying data set, we should not be calling this mechanism privacy preserving. Okay. Dinur and Nissim also showed us that it's fundamentally impossible for any mechanism to answer all queries accurately and maintain privacy. And this may sound obvious to you, but actually this is sort of devastating news to folks who at the time, or even still, harbor this hope that it should be possible to do something like take a data set, sort of scramble it a bit and release it such that the released version is good for all queries that you might possibly be interested in, but yet preserves privacy. And what this result says is, no, that's not going to happen. So in particular, the Dinur and Nissim statement is in terms of these sort of normalized inner product queries. And the statement says that if you're going to answer all inner product queries to within some particular alpha accuracy level, then those answers allow you to reconstruct the vast majority of the data set. So that's pretty bad news. You can take this bad news even a step further, and they also show us that answering just and randomly chosen inner product queries with some sort of order of root n accuracy also already allows reconstruction. And actually, the sort of negative results have been taken even further. I won't go into detail, but basically, you can also reconstruct even if only slightly more than half of your queries are guaranteed to have this order of root n error. And the rest of the queries are allowed to be arbitrarily wrong. Also, work of Dwork, Sherry, and Talwar show how to make this reconstruction process efficient. So this is sort of really bad news for anybody who's hoping to answer a lot of queries and give some interesting, reasonable guarantee of privacy. So against this backdrop, sort of improved and sort of finally some rigor to understanding what is privacy not, the notion of differential privacy emerged. So the definition of differential privacy, or a version of it, first appeared in this paper of DeWolf, McSherry, and Smith from 2006. And what it is it's a requirement of a mechanism. It's a restriction on the behavior of a mechanism. What does differential privacy say? Well, epsilon, comma, delta, parameterized differential privacy, is a guarantee that requires that your mechanism on any two neighboring data sets that differ in just one person's information are going to induce almost exactly the same distribution over outcomes. So you can think of this as sort of a stability requirement of your mechanism. It says, even if I were to slightly perturb the input database, the distribution over outcomes would look almost the same. And look almost the same is in this particular differential privacy sense of closeness between the two distributions. So in particular, what it says is that for any subset of the outcome space that you might be interested in, the probability that the mechanism is going to map your first database to that subset of the outcome space is very, very close to the probability that the mechanism is going to output any neighboring data set that differed in just one person's information to that subset of the outcome space. And that very, very close has both an e to the epsilon multiplicative factor on it. So that was the epsilon parameter on the differential privacy. And we also allow ourselves an additive delta change in the probability. And that was that delta parameter in the differential privacy definition. Okay, so this is a notion of stability that says that when we change the underlying database, that the distribution over results shouldn't change very much. This is natural to sort of interpret as a privacy notion, because from the perspective of an individual, what it says is, if I know that my data is in a database that's going to be treated with differential privacy, or that all mechanisms that will be run on my data on this database will be with differential privacy guarantees that I find appealing. What this tells me is that actually any possible future world that I might be concerned about, any possible future outcome or impact that I might be worried about as a result of this computation, it's going to occur with almost exactly the same probability, regardless of whether or not I provide my data or whether I falsify my data in the database. So you can formalize this. This means from the perspective of an individual that my utility is not substantially affected, regardless of whether or not I participate in the computation. So this is quite a strong guarantee.
Katrina? There is a question from Kevin.
Yeah.
I'm immediately prompted to ask a question. I assume your model consists of identifying a data element Si as belonging to person I, but in social network dataset, the data about person I often contains information about the relationship to other people. I think the underlying issue is whether it is important to model relational databases.
Absolutely. So in the real world, we've come to all realize that there's no such thing as personal data. There's no such thing as data that pertains only to me and is relevant only to me and can harm only me. That's absolutely true. For now, we're going to set that aside and think about each person's data as pertaining to them. As I will tell you on the next slide, if you're willing to have your model be that each piece of data is relevant only to a small number of people, then everything I'm going to say here is basically still going to be relevant and still going to hold. But if you're dealing with a data set in which every single row actually is relevant to basically everyone, then that's not the right context for these kinds of lessons to be drawn. I'm not going to go deeper than that, but it's a great observation. Thanks for the point.
It's sort of the difference between a sparse graph and a dense graph.
Yeah, so I mean, so think about it as this isn't graph structured data. This is, medical records where yes, my medical data is relevant to my close relatives, but it's less relevant to, the person who lives in the next county. It's not, not perfect, but a reasonable approximation is that my medical data is relevant mostly to a small number of people.
I apologize for asking a question so early, but I think for students, asking questions about the model is one of the most important things, right? Because changes to the model lead to new kinds of results.
Absolutely. Yeah, I'm happy to take questions at any point, so go for it. Okay, so just to get comfortable with this definition a little bit, if you haven't seen it before, it's probably a little unfamiliar. If you have, you're probably bored, but I'll tell you to wake up in a minute. So differential privacy, again, I'm going to emphasize this, can be interpreted as a stability notion of the computation. It says the computation that you're doing is robust to small changes in its input in the underlying data. And robustness or stability of this sort is nice, not just as a privacy notion, but it generally sounds like a pretty good thing for a computation to have. Think about it. If you're doing science, you're doing some sort of scientific study, you would probably be pretty uncomfortable if your results would have changed dramatically had one person not shown up for the study. That's probably not good science. Similarly, if you're doing machine learning and the choice of model is incredibly driven by one data point, that's probably not going to be a good choice of model. It's probably not going to generalize. And this is just to sort of foreshadow the connection that we're going to see shortly. Okay, so we have this differential privacy notion. For now, we're thinking about it as a privacy notion. But in the back of our minds, we know it's really sort of about stability of a computation. So now what I want to do is tell you a little bit about some of the nice properties that differential privacy has, which I think are deeply part of the reason why this notion has gotten so much attention over the past sort of decade and a half. Okay, so briefly and at sort of a high level, I'm going to tell you about 3 properties of differential privacy. The first is that thing that I just hinted to on the previous slide, that if you have a mechanism that enjoys a guarantee of differential privacy, it also immediately enjoys a stability guarantee that degrades slightly, but with respect to changes not just in one row in the database, but in a small number of rows. So if something's differentially private, it's robust not just to changing one row in the database, it's also slightly less robust to changing a small number of rows in the database. And you have nice controls on how that robustness guarantee degrades. The second nice property of differential privacy I wanted to mention is a post-processing guarantee. And what this says intuitively is that if you do a computation with a guarantee of differential privacy, and then somebody comes and looks at the output and thinks really hard about it and matches it up with some additional information that they happen to have, no matter what they do, so long as they don't go back to the original database, that subsequent thinking, processing, computing cannot degrade the guarantee of differential privacy. It can only make it stronger. And that is really an extraordinary guarantee to have when compared with other sort of more ad hoc notions of privacy that were previously used in the literature. Differential privacy is a guarantee where you can give it, run it, and go home and sleep well at night. You know that when something is differentially private, it's differentially private now and forever. It doesn't depend on some assumptions about what an adversary will and won't do. And then the third property—
Kevin is asking about the definition of neighbor.
Yeah, so okay, so if you've seen differential privacy before, you've probably often seen it written with the notion of neighboring databases being adding and removing one individual. For the purposes of this talk, I'm going to use the alternative definition of changing one person's data. If you think about it for a moment, you see that the adding or removing one person version of the definition implies the changing one person's data definition with a factor of 2 introduced. The other implication is not immediate. In many cases, you can get around this, but for simplicity, for a number of reasons, I'm going to focus on the sort of fixed database size version of the differential privacy definition. So we're going to have databases of size n, and neighbors are going to be, we change one row. Thanks for pointing that out. Okay, so the third property of differential privacy that I want to point to here is a composition property. What do I mean by this? Intuitively, what I mean is that if I do some computation that's differentially private, and then I do some other computation that also has a differential privacy guarantee, that I have a way to reason about the privacy loss of the combination of those computations. And loosely, in its simplest version, what composition theorems say is that the privacy harms add up. And what this does for you is it's very convenient. Because of composition properties, this allows us to design small differentially private components, small algorithms, and then assemble them into much more complex algorithms. And this is exactly what happens in the literature. And then the privacy properties of those more complex algorithms are basically inherited directly from the privacy analyses of the small components. So composition actually, it turns out, there's sort of a stronger version than just the privacy harms add up. And that stronger version is going to be somewhat important for us today. So I'm going to spend a little bit of time talking about it. So the composition style theorems for differential privacy sort of accumulated in the literature through a series of papers. Early on, sort of the ideas of composition first appeared in work of Denoy and Nassim, that paper that I mentioned before, and a paper of the work of Nassim from 2004. And the sort of formal statement of the type of composition theorem that I'm stating here first appeared in Dwork, Rothblum, and Verdon 2010. So this theorem that I'm about to give you, it takes a little bit of parsing and it has two twists in it at once. And so we'll break those apart and understand them a little bit better. What the theorem says is that if you have a sequence of k differentially private mechanisms where each of them was epsilon delta differentially private, the composition of all of those mechanisms together enjoys a guarantee that looks something like epsilon times not k, but square root of k, comma k times delta, plus some delta prime that's used to do some sort of fudging between the epsilons and the deltas. So that's the first thing that I'm pointing to in this theorem is, wow, the privacy harms add up not linearly in the number of computations, but actually in the square root of the number of computations. That's pretty awesome. The second thing to point out in this strong version of the composition theorem is that you're allowed to have subsequent choices of queries depend on the results of previous choices of queries. So you're allowed to have your composition be adaptive. So that means that that analyst is allowed to look at the results of the previous queries that came out from the mechanism box and use those in part as the basis of choosing what query to issue next. And that's going to be really crucial for us. Where does that adaptivity sort of guarantee come from? Essentially, because the basis on which the analyst is picking its next queries is the results that it's gotten from the mechanism, because those results were not very revealing of the underlying database because it was differentially private, that limits the extent to which actually the future queries can depend too much on the underlying database. And so this adaptivity ends up being okay for us for this type of theorem. Where does this sort of sublinear harm aggregation come from? Basically, the idea here is that the expected privacy loss is actually much better than the worst case privacy loss. And so you get sort of a martingale analysis to get sort of concentration here. Okay. So for today's talk, we're going to be talking primarily about linear queries. The results generalize beyond that, but we'll focus on this already pretty rich class of queries. And you can use them as the building blocks of much more sophisticated algorithms. So what's a linear query? A linear query is one that takes a database element and returns a value between 0 and 1. And when it's issued on a collection of database elements or a database, what it does is it returns the average value that it obtains across the elements of that database. Okay, so that's just a linear query. These are going to be the types of queries we're talking about for the remainder of the talk. So I need to tell you, what can differential privacy do for linear queries? There's sort of a slightly more naive version of the statement that you can get just by applying already the composition theorem that I told you. But I think the best analysis that I know is from this paper of s-19 and Ullman from 2016, which basically the important point to take from here is that if you issue a sequence of queries, that the error is going to grow as the square root of the size of the set of queries. Or interpreted another way, you can say you can answer approximately quadratically many queries if you're willing to see constant error. And that sort of quadratically many queries is going to be sort of a recurring theme for the talk today. And it's important to note that this is essentially optimal if the data universe is large, unless the answers are really in sort of a strange way coordinated based on the queries. So not going there today, but if you do have a small data universe, that in some sense forces your queries to have some implicit relationships, some sort of underlying structure, and then you can leverage that structure. We're not going there. We live in the sort of large data universe world for the purposes of today's talks. And so really this idea that we can answer quadratically many queries is the best we can do. Okay. So that was differential privacy. Now we're going to sort of take a deep breath and see something new. And that's the problem of adaptive data analysis. So this cartoon that I drew you before, where we had sort of a data set and then we were issuing queries and answering queries on that data set, I want to convince you that basically this is a pretty good cartoon depiction of how science works. Or if it's hard for you to imagine what is science, how machine learning works. So basically, in science or in machine learning, we imagine that there's some true underlying distribution over data, where those data points could be, people or whatever physical phenomena it is that you're observing. But generally, scientists don't get access to the underlying distribution, and science is done on a sample. And so what you do is you get access to some sample from the true underlying distribution. I mean, you hope it's a sample from the true underlying distribution. Let's set that aside. And then you try to understand stuff about it. And you hope that that tells you something about the true underlying distribution. But naturally, when you do science, there's this sort of aspect of adaptivity. The hypothesis that I put forward today naturally was chosen by me, in some sense, as a function of the previous scientific results that others have put forward. And in machine learning, that next step that I take of my gradient descent algorithm is quite naturally dependent on the results of the previous queries that were issued. Okay, so I want to convince you this is a pretty decent cartoon for, in some sense, how science and machine learning go. Is that we ask questions and we answer questions, and sometimes we learn things in the process, and that affects which questions we ask next. Okay, so what do we want from our science or from our machine learning? Well, a lot of times we somehow convinced ourselves that what we want is sample accuracy. We want to somehow answer the questions well on the data sample. But really what we want from our science or from our machine learning is we want distribution accuracy. We want to answer the queries in some way that actually is close to the true answer on the true underlying data distribution. The reason we go around talking about sort of sample accuracy and assessing things properly on the sample that we have on hand is because that's what we have. We have the sample, we don't have the distribution. And the hope is that doing science on the sample is still relevant for the distribution. So we have these notions of alpha beta sample accuracy and alpha beta distributional accuracy. And each of them just says that there's some beta probability of failure, but other than that, you're going to be alpha close to the correct answer, where in one case, the correct answer is the correct answer on the sample, and the other case, the correct answer is the correct answer on the distribution. So that's what we're trying to get distribution accuracy. We're trying to get at the true answers on the underlying distribution when we do science or when we do machine learning. Okay, the problem is we have only a sample. So the question is, what are the tools that are available to us as scientists who have to do science on the sample? And for now, let's set aside the fact that science is super adaptive and just think about the simple world in which we have one query that we want to issue against our sample. And we're trying to figure out what are the chances that that query is telling us something useful about the underlying data distribution. So one tool we have in our toolbox is just a Chernoff bound, which in some sense tells us exactly that. It bounds the probability that the answer we get on a sample is very different from the answer we get on the underlying distribution. And one of the cool things here is that that failure probability is exponentially small. Now, again, still setting aside adaptivity, this can be interpreted in the context of linear queries to say that for any data distribution, if I take a sample from that data distribution and issue my linear query of interest, then with high probability, the difference between the value that query is going to take on my sample and the value it would have taken on the distribution is going to be quite small. And quite small in what sense? Well, it's going to have this sort of square root of n kind of a dependence to it. And you notice there that 1 over delta or that 2 over delta is inside a log. Okay? What if I wanted, though, to answer more than one query on my data set? Again, it's still in the world where these queries are non-adaptive. What can I say about the underlying distribution when I only have access to a sample? Well, here the idea is just apply a union bound across your turn-off bound. So now we can say if we have some fixed sequence of k linear queries, then except with small failure probability, the worst of these queries in terms of the difference between the value it gives on the sample and the value that it gives on the underlying data distribution is going to be not too bad. And again, we have a very similar term here. We still have that sort of square root of n kind of a relationship, but now that k, the number of queries we're issuing, shows up. But beautifully, that k shows up inside the log. And so the way to interpret this is to say, wow, we can issue exponentially many queries in the relevant problem parameters and be guaranteed that doing those exponentially many queries on the sample is going to be telling us relevant stuff about the underlying data distribution. Okay, but that was when the queries were fixed in advance, not chosen as a function of the database of the sample. So what if we allow that kind of adaptivity? What if the query can actually be a function of the data? Well, clearly, if the query is allowed to be a function of the sample that we have, we're in serious trouble. Because then I can just go and define a query that returns 1 when it gets a point that's in our sample set and 0 otherwise. And pretty clearly, that's a query that's going to behave very, very differently on the, say, uniform distribution than it will behave on a sample from the uniform distribution. So clearly, we get terrible overfitting. We can pick really bad queries if we're allowed to pick them directly as a function of the data sample. But you're saying, give me a break. Who's picking their science to do? Who's picking their next step of their machine learning algorithm directly as a function of their training data? Nobody's doing that, right? So what if the queries were chosen not as a function of the sample, but as a function of the answers to previous queries? Can we still get ourselves in trouble? And the answer is, unfortunately, yes. It just takes one query. I mean, depending on how you set up your query language, it takes just a limited number of queries to basically have your query answers encode the data set. And then you're sort of off to the races again. Your next query is allowed to arbitrarily overfit. So for example, if our data points are natural numbers, we can set our query to just do this encoding. So it returns on a data point 1 over 2 to the x. And then when you issue this against a data set, what you're basically doing is you're encoding the data set. You're encoding its histogram. And there are various versions of this that you can do, but the point is, okay, if we're not careful about what queries we allow, we can get ourselves in serious trouble. And then subsequent queries, we have no guarantees that they're going to be relevant to the underlying data distribution. Okay. But nobody's trying to encode the data set, of course, right? When you do science, your goal is not to encode your sample, it's to actually do science. So what about sort of more natural looking analyses? So here, let's use an example where suppose what you have is your data domain is labeled examples. So the examples are like, D bits, and each of them has a label of 0 or 1. And your goal is to do classification. So you want to come up with a function that, given a point, is pretty good at predicting what its label is. So here's a natural approach that you might want to take. First, you try to figure out which of the coordinates are actually sort of relevant for predicting the label. So to do that, you just compute the correlation between each of the coordinates and the labels. And you say that a coordinate, a feature, is predictive if it's got sort of somewhat better than 1/2 correlation there. And so then we take all of those predictive features and we say, take the majority of them and call that our function, okay? So, given a new point, what we do is we just check against each of the predictive features, the ones we labeled before as being useful. We just check sort of what's the majority vote and we do whatever it says, okay? Sounds like kind of a reasonable thing to do, and it's closely analogous to things that people actually do with data. Turns out, how does it perform? Well, one thing you can do is you can compute the performance of this function. You can compute it on the sample. It's going to look pretty good on the sample, probably. But how's that going to compare with how it looks on the underlying distribution? Well, say, for example, your data distribution is uniform data, uniform labels, then it turns out there exists some constant C such that with high probability, as long as the size of your data points, your D, is big enough, and it's not that big that we're asking for here, then actually the way this function performs on your sample is going to basically be as bad as possible when compared with how it performs in the underlying data distribution. So basically what's happened here in summary is even with good intentions and kind of benign looking actions that we've taken here, we manage again to encode the database in our answers to the queries. And then again, you're off to the races. You can overfit arbitrarily. Okay, so how are you supposed to do science on a sample? What's going on here? In some sense, what's going on here is the reality that this adaptivity is allowing us to search through a tree of possibilities. So these adaptively chosen queries are letting us not just pick sort of explore a linear path, but in some sense, we're exploring exponentially many queries because of this adaptivity. And we see adaptivity causing problems, not just in the machine learning world, but in data-driven science broadly. And if you've sort of been paying attention to sort of science news over the past decade, you've noticed basically every data-driven field experience a crisis of reproducibility. And adaptivity is not the only reason for these crises of reproducibility, but it's a major one. Okay, so how are we supposed to do science on the sample? Because we want that adaptivity. Adaptivity is really powerful. It's really makes a lot of sense. So one solution is don't reuse your data. So every time you issue a query, you need to gather fresh data for it. Or thinking about a different way, take the data that you have and split it up into little pieces and use each piece just for one query. Then your queries won't be adaptively chosen and you don't have any problems. The problem that you have is that now your database size has to grow linearly with the number of queries you want to issue. There are other toolkits, they're pretty limited, but I'll mention just in passing and then we won't go into depth in this. One toolkit you can use is compressibility. So if your mechanism's output is compressible to just B bits, then a deterministic analyst can only ever explore 2 to the B queries. So if you have a very limited language of what you're outputting about the database, then that does help you with regards to adaptivity. Well, we'd like to do something sort of richer and better than that. Okay, so now what we want to do is we want to take those ideas from differential privacy and use them to help us understand this adaptivity problem a bit better. So again, to remind you, we have this notion of differential privacy, stability notion of a computation that says that a change in the underlying database, meaning changing one person's information, changing one row of that underlying database, isn't allowed to have a substantial impact on the distribution over outcomes that's induced. And now, what I want to do is I want to give you the punchline for the paper, and then we'll sort of build up to this. This is a punchline that builds on a long line of work. The connection between differential privacy and adaptive data analysis first appeared in a series of papers by Dwork, Feldman, Hart, Potassi, Reingold, and Roth in 2015. A subsequent paper of Basili, Nassim, Smith, Steinke, Stemmer, and Ullman gave us new tools for reasoning about this connection and better results in this space. All of these were against the backdrop of some impossibility results of Hart and Ullman and Steinke in Ullman in 2014 and 2015. And the actual results that I'll be presenting here appeared in that paper I mentioned at the beginning of the talk. So what's the statement that we can make? The statement says that if you have a mechanism that's differentially private and it's sample accurate for linear queries, then you immediately get a guarantee of distribution accuracy. So if you have something that's differentially private and it's sample accurate, then it's immediately distribution accurate. And so what this means is those lessons that we learned about how subject to differential privacy, we can answer sort of quadratically many queries, those immediately apply here to say, even if you don't care about privacy, if you use differential privacy as a tool to prevent you from overfitting, that you can answer quadratically many adaptively chosen queries on your data set. So maybe sort of to put that another way, in some sense, we have three quantities that are around here, and we have sort of three terms that allow us to talk about the relationships between those quantities. So we have the Holy Grail, which is we'd love to be able to answer all of the queries that are issued according to the underlying distribution. That's the thing at the top. That's what we wish we had, but we don't know the underlying distribution. Instead, what we know is a sample. So when somebody issues a query, when the analyst issues the query, what M actually has access to is what value does that query take on our sample. If we could guarantee that those two values were close to each other, we'd call that generalization. That means that what we do on the sample generalizes to the underlying distribution. The other thing that we have is we don't have to give the analyst the correct answer on the sample. We can add some noise or perturb it somehow. And so we have the ability to, instead of giving the analyst direct access to the value of the query on the sample, we can give it something else, that M of S comma Q, whatever the mechanism wants to output. If the thing that we say and the true value of the query on the sample were close, we'd call that sample accuracy. And our goal is that the thing that we say is actually close to the true value of the query on the underlying distribution. We call that distribution accuracy. And so you can see we have sort of a triangle inequality thing going on here, where if we could guarantee generalization and sample accuracy, we would immediately inherit a guarantee of distribution accuracy. The problem is there's a tension between generalization and sample accuracy. The more we tell the analyst about the correct answer on the sample, the better our sample accuracy is, but the more that allows the analyst to issue overfitting queries, because the analyst learns more about the sample. And the more that the analyst can issue overfitting queries, the worse we are on generalization. So there's a tension here, and what we're trying to figure out how to do is how to simultaneously get that generalization and that sample accuracy guarantee. So the intuition that we're going to use to get both of those at once is that in some sense we need to control how much the observed behavior, so the sequence of query, answer, query, answer, query, answer, could change someone's beliefs about the data sample that we have on hand. And so a useful quantity for us for reasoning about this is going to be, given that transcript of observations, some transcript pi, we're going to write Q sub pi for the posterior distribution on data sets conditional on pi. Now, Q sub pi is not something that the mechanism actually knows. It's not necessarily something that the analyst actually knows. In order to compute it, you would actually need to know the underlying distribution, but it's still going to be a useful analytical tool, the idea of this posterior distribution on databases, okay? And so given that posterior distribution on databases, we can now introduce a couple of other concepts that are sort of analogous to the previous two we just lined up. So the first of these is posterior insensitivity, which says that on the queries that are actually issued, we want the value of those queries on the true underlying distribution to be close to the values they take on that posterior distribution. And then the other one is posterior accuracy, meaning that the answers that we give to those queries are actually going to be close to the values that those queries take on this posterior distribution, sort of the induced beliefs about the database that we have on the basis of divisible query answer pairs. And so now this allows us to take that triangle that we were reasoning about before and do a different version. And it turns out we can sort of, instead of talking about in the bottom right corner, that Q of S value, we can instead reason in its place about Q of this posterior distribution. And this leads us to talk about two different quantities, the posterior insensitivity in place of the generalization, and the posterior accuracy in place of the sample accuracy. And so the new sort of approach that we take here now is to say that if we could give ourselves a guarantee both of posterior insensitivity and of posterior accuracy, then we would inherit a guarantee immediately of distribution accuracy. And that's exactly the theorem that we show. So we show that if you have a mechanism that's posterior insensitive and simultaneously is posterior accurate, then it's immediately distribution accurate. And so now in order to actually apply that theorem, which you just get by the triangle inequality, we need to prove those two pieces, the posterior insensitivity and the posterior accuracy. So the sketch of the proof is two pieces. First, we show that if you have a mechanism that's sample accurate, then it's also posterior accurate. And secondly, we show that if you have a mechanism that's differentially private, then it's posterior insensitive. And that'll mean that if we have a mechanism that's sample accurate and differentially private, then we're going to immediately inherit this property that the answers that it gives are going to be close to the answers on the true underlying distribution, which is exactly what we wanted. Okay, so given time constraints, I'm going to treat these lemmas at a very high level, just sort of give you the flavor of how they're proved. So the first lemma is that sample accuracy implies posterior accuracy, or in particular, alpha beta sample accuracy implies alpha plus C comma beta over C posterior accuracy for any C that you want to pick to do that trade-off. And the way we argue this lemma is using sort of a key idea, the sort of Bayesian resampling lemma. And I remember the precise moment at which Aaron suggested this idea exactly where we were standing, because it's such a sort of cool trick. The idea here is that you imagine after that interaction between the mechanism and the analyst runs and yields some transcript of query answer, query answer, query answer, imagine that after that, you resample the data set from the induced posterior, that Q sub pi over data sets. And the point is that this resampling actually doesn't change the joint distribution on data sets and transcripts. And this ends up being sort of a clever tool that we can use to do sort of a swap in the proof. And so the pieces of the proof, once you have that, are really simple. Basically, it's an application Markov's inequality, things we obviously know based on the fact that we assumed that we had sample accuracy, and then this Bayesian resampling trick. Okay. So obviously that was too fast for you to get all the pieces, or I hope that was too fast for you to get all the pieces. But you should really see that it's just a few lines to get the connection at that point. The other lemma that we needed was this implication that differential privacy immediately gives you a guarantee of posterior insensitivity. Or in particular, if you have something that's epsilon delta differentially private, you can immediately say that it's e to the epsilon minus 1 plus 2 d comma delta over d posterior insensitive for any positive d that you pick. Okay, so this one I'm going to do at even sort of a higher level. But the sketch of it is, you sort of notice that there are certain transcripts, certain sequences of query answer, query answer, query answer, that induce a posterior Q sub pi, so beliefs about the data sample that you actually have that are bad, in the sense that there are queries in that transcript on which the posterior behaves very, very differently than the underlying distribution. So the difference between that query on the posterior versus on the distribution is big. And then you have to observe that actually, if you can ensure that the joint distribution on data points and on transcripts, if you can ensure that that joint distribution is not too different from the product distribution between data points and these transcripts, then actually that is enough to show that these bad transcripts are not going to be too likely. And then the final piece is just to show actually that differential privacy, in fact, ensures for you that the joint and the product distributions are close to each other. And intuitively, why is this? Well, differential privacy is promising you that if you were to change a single data point, that wouldn't change the transcript by very much. So it's perhaps not surprising that it says that the joint and the product distributions behave similarly. And so that's the final piece of the proof here. And you put it all together to get this final implication that differential privacy plus sample accuracy really gives you that distribution accuracy that we were after. And so the implication is that now we can do more in the face of adaptivity. Okay, so what's next? What do we, where do we go from here? What does this all mean? So just to summarize, we learned in the world where nothing is adaptively chosen and all of the queries are fixed in advance, you can answer exponentially many queries. It's amazing. In the world in which there's adaptivity, things are just dramatically different. So you have the option of sample splitting, and then you get linearly many queries, or you have the option of differential privacy, and then you get quadratically many queries. These differential privacy guarantees, of course, are asymptotic guarantees. The current analysis that I showed you sort of starts to kick in for relevance. I mean, depending, of course, on all your parameters. On the scale of tens or hundreds of thousands of data points, you start to prefer using differential privacy to doing sample splitting. So it's, maybe entering the realm of sort of relevance actually for working with real data. But, and as I mentioned before, this is in a sense tight. So in the worst case, these results of Harden-Ullman and Seiken-Ullman say basically, you're not going to do better than quadratically many queries. So, okay, so why do I say there's a what's next? You should have in your gut this feeling, but, differential privacy, it's so worst case. It's worst case over all neighboring pairs. It's worst case over all outcomes. It's worst case over all data distributions. It's worst case over all analysts. But I didn't care about worst case. This is not a talk about privacy. This is a talk about statistical validity. Statistical validity is an average or a high probability kind of a statement. It's not a worst case kind of a statement. What was all this worst case stuff about? And in particular, that thing that I'm doing on my data, it's not worst case. Can I say something about that? Okay, so what can we do to step away from sort of all of this worst case, worst case, worst case, worst case? So one answer to sort of this, isn't this all overkill, is yes, in some sense. So Moshe Schenfeld and I have a paper in Lester's Neurops where we show that yes, you can relax differential privacy to be a less worst case, but very similar notion, and still inherit all of the sort of results about robustness to adaptivity. But it still sort of butts up against this, differential privacy was in the worst case optimal, so it's not better, it's just weaker than differential privacy. The other direction to go in or think in is, well, so what if I'm willing to assume something about my data distribution? And so what if I'm willing to assume something about my analysts, that they really aren't worst case? And there is where I think there's really the opportunity to push forward and do something more, something interesting. Because I have the sense that these theoretical bounds are not really yet touching on the practical adaptive data analysis that's actually happening on data in the day-to-day. And we somehow need to figure out how to bridge that gap, both so that we can start to explain why it is that in the real world, often there isn't overfitting, when in some sense the theory would have predicted it, but also so that we can start to offer more and more relevant and useful tools for mitigating, for measuring, for controlling the impacts of adaptivity and ensuring that the science that we do on our data is as accurate as possible, and we're making the best use of the data that we can. One lesson that I sort of take from all of this type of thinking is that it's really, really important to change how we think of data as a resource. I think there's this pervasive view that data is sort of a boundless fountain, and you can keep using the data for as long as you want, and there's no penalty to pay. And that's really, really not the case, both in a privacy sense, because the privacy harms add up as you do more computations on a data set, but also in a statistical validity sense. Data is a limited resource. It's something that you spend. As you issue queries and computations against a data set, that data set becomes less valuable. And I think that's a really important sort of shift in how we think about things here. So I'd point your attention in particular to, how can we think formally about non-worst case analysts? Moshe and I have been doing some work on this. Next time you invite me, I hope to tell you about that because I think there are some really exciting things to say there. But that's the bottom line that I'd like you to take away. That differential privacy sort of magically has this beautiful connection to adaptive data analysis. The data is something that we spend. There's this huge gap that's forced by adaptivity. That doing adaptive data analysis is much more harmful than non-adaptive data analysis, and that there are some interesting questions still to be addressed. Thanks.
So after the virtual and real clapping, questions. Okay, here's a question from Rohit Chatterjee. Is the shape concentration of the true distribution the most crucial thing here? Or is it probably more involved than that?
I'm sorry, I missed a word, but maybe I can actually also look at the chat. I couldn't hear them. So I actually think the true data distribution is probably less, in some sense, the issue than the queries that are issued against it. That you're going to get more
the joint
power.
shape?
Pardon?
The joint shape or of the?
Okay. Sorry. Maybe I misunderstood the question. I took the question to mean, is the exciting next thing to do to make assumptions about the data distribution or to make assumptions about the queries? And I think it's more to make assumptions about the queries. I could be wrong. Maybe another way to interpret this question, which is maybe also a good way to interpret it, is I sort of what, is really the crucial concept here. These sort of various versions of the data distribution that are conditioned on various things, like the observations that you're seeing as a result of this interaction between the mechanism and the adversary. And in some sense, yes. In some sense, we can, in this alternative relaxed version of differential privacy, we can actually construct, in some sense, bad examples from this that in some sense show that this is really sort of a tight notion and this is sort of the crucial notion to be tracking.
Okay. Other questions?
I see Kevin has a hand up.
Yeah, actually, because I'm co-host, I can't raise my hand. And
Go for it.
I have this reputation of always annoying job candidates when they start giving their talk because I immediately start asking about the model. And a lot of the job candidates were like, my advisor told me what the model is. I didn't question that. But in your model of adaptivity, if I understand it correctly, the queries can depend on the data. You're trying to address the question of where the queries depend on the data.
Yeah, so the queries can depend on the answers to the previous queries.
Okay, so in some data sets, they're extremely dynamic, and the kind of questions that can be asked will actually be predictive of what the data will become. So if you think of a click log, I worked at Google for too long, so I think of those. When you ask a question, will a user click on this link? That's sort of predicting that there will be a data element that enters the log for that, the set of choices they had at that time. Another example would be if the query was, will this person transmit COVID to somebody else, right? There's a whole bunch of dependencies here, right? That if you're even asking that question, maybe there's a possibility that it could happen, right? It's strongly correlated to the data, and then a data element will enter the data set, and then the next question is likely to be, what about the other people that are physically located there? And so I'm wondering if your model should incorporate the fact that there's correlation between the queries and the data, and that the data is also changing. So for example, if you look at predicting on Twitter, old tweets don't get clicks, only new ones do. The only interesting data to look at is the recent data.
So I think there are multiple interesting questions embedded in your question. So let me try to pull a few of them out and address them separately. So one of them is this question of, shouldn't the model reflect the fact that the queries that I issue are based on some sort of understanding of where the data is coming from? In some sense, yeah, the model already has that baked in. The type of reasoning that we're doing still holds up if the analyst actually had access to the data distribution or had access to some other functions of the data distribution. The problem is if the analyst has access to the sample. That's the thing we have to protect. And so the way that we model the analyst having information about the sample is having issued queries about it. And you can interpret queries very broadly there and learn stuff about it. So that's sort of one piece of like how you model this thing. But another thing you raised that I think is really important and interesting is databases in the real world that we care about are not static. And that's somewhat outside of the model here. I absolutely agree. And it's potentially a source of real problem, both for privacy and for statistical validity. Intuitively, the reason for this is if I issue a query on a database, and then one point is added to the database, and then I issue the same query again, even though both of those queries maybe look totally innocuous, the difference between their values can be very, very revealing. And this is problematic if you're trying to avoid either revealing stuff about the data set, or if you're trying to avoid overfitting to the data set by revealing stuff about the data set. So that dynamic data aspect is not modeled here. It's really important. It's worth talking and thinking about more. Yeah, thanks for the questions.
Good stuff for your students.
Yeah. So Katrina, another question. I don't know if you were present. So David Woodruff gave, also a great talk on adversarially robust sketching, and I couldn't help. There seemed to be, I don't know if you're familiar with this literature, but basically, if somebody can give, depending on your answers to the current sketching in low memory, whether somebody can give you adversarial data to screw you up, basically by learning your randomness and so on. So it seems like the kind of technique that they use, if they translate it to differential privacy, would be, one, you can use your data or your ID samples slowly. So maybe first you will answer on a little bit on these users. When you run out of the budget, you will slowly move to another user's set. So rather than always give you the answer on the entire database, you will ration it and move it slowly. This is one technique in the use, but of course this only works for kind of queries where the answer doesn't change too wildly. Like if you maintain some kind of average or something like that, which was the case for the sketching scenario, I guess. Do you know if there is any connection, and maybe those two techniques where maybe you will restrict the analyst not to change questions too crazily, maybe from one query to another query, and also slowly using your data set? Do you think there is something maybe more formal or some connection here?
So there's been very little sort of exploration that I know of explicit connections there, but it's always sort of felt like there was an opportunity to do more and say more. There's certainly differences in the model, at least as I reason about it. I mean, Moni, you look like you were about to say something. Were you going to say something explicitly about a connection there?
No, just there is a subsequent work. I don't know if David mentioned it, that did use DP.
Yeah, so I mean, there have been a few points of connection
An advanced composition.
Yeah.
I don't remember the precise authors, so I'm hesitant to say.
You mentioned both the subsequent work and the subsequent work that improves over the subsequent work.
Okay.
Yeah.
So unfortunately, I didn't see the talk, so I don't have all of those reference points. But yeah, there have been points of connection. It feels like there should be more. I think that's a very natural sort of analogy to draw. Yeah, definitely.
But maybe going in an opposite direction, I guess David used it for sketching a scenario kind of techniques from differential privacy, maybe for this adaptive data analysis, but specifically those two ideas, which I'm just naively inheriting from his work, that don't use all your data right away, slowly ration it as you include more sample. So kind of while you know that the analyst doesn't know too much, uses exponential bound, and slowly as you kind of leak data, get more information. and then maybe under some assumptions the queries don't change too crazily, like that you are still studying like COVID vaccine and not something like from tuberculosis. I mean, like totally crazy things. So those techniques, have you guys used it in this adaptive data analysis? So these two ideas?
So there is some work that has a little bit of a flavor in common in the following sense. There's work that attempts to give sort of adaptive data analysis types of guarantees that thinks about it as, let's use the data that we have, spend down the statistical validity that it has available in it, and then buy a fresh data set once we've spent that down. And then we're going to buy a bigger fresh data set. We're going to spend that next one down. And the motivation and sort of perspective from that type of work was actually thinking about what if we actually had a bunch of different research groups sort of sharing access to data and collaborating on a data set. We would need some tools to try to figure out, how to charge everybody for the, statistical validity that they wasted in the data set. So there's been some interesting work that tries to figure out sort of how you do this sort of tracking and how you sort of spend the data over time. But in some sense, we don't have, this is not exactly true. There are very limited places in reasoning about differential privacy where using a subset of the data intentionally has been powerful. And that seems in my mind to be sort of a distinction. We tend to use all the data and add noise rather than use some of the data. That's not quite universally true, but almost.
Nice, thank you. Yeah, it's interesting stuff.
Thanks for the questions and the connections.
Other questions? Okay, going once, twice, thrice. Thank you very much, Katrina, for the great talk. And thank you for the audience for the questions.
Thank you.
And
Yeah,
see you in TCC, in the whatever workshop we'll have in TCC 2021. Thank you.
Thanks, everybody. Take care. Hope to see you in person